Happy Saturday, everybody. I'm just making this quick video to show you a trick on how to approach showing that one function is big omega of another function, specifically for polynomials. So let's review what big omega means. So we have f and g are positive real value functions. If there exist constants c and n naught that are positive real values, such that f of n is greater or equal to c times g of n, for n is greater or equal to n naught, then f of n is big omega of g of n. So conceptually what we're saying is that f of n has a lower bound that's some factor of g of n. So let's start with an example. So let's say f of n is 7n cubed minus 50n minus 20. And we want to show that f of n is in big omega of n cubed. One giveaway that this is true is that we have a polynomial of degree 3, so therefore it's going to be big omega of a polynomial of degree 3. Okay. Alright, so let's approach this using a method that's a little bit algorithmic, but will get us the answer. So the first thing we need to do is set this up to figure out what values of c and n naught we need. That's our goal. What is c going to be and what is n naught going to be? Okay, so we know what we need to do. For this example, I'm going to find out what n naught is first. And I'm going to determine what n naught is by using this algorithmic approach. So I'm going to set n naught equal to a specific value, and the value is going to be created using the coefficients in f of n. So I'm going to take the coefficients on the non-leading terms in f of n. So our non-leading terms are negative 50n and negative 20. So I'm going to take those coefficients, negative 50 and negative 20, make them positive. So 50 and 20. I'm going to add them together. So we're adding the absolute value of the coefficients. And then I'm going to divide it by the leading coefficient, which is 7. And then after we do that, we're going to multiply that all by 2. And so I'm going to set n naught equal to 20. So from here, we're going to figure out what the c is. So we said n naught is 20. Okay. So we need to show an inequality in our definition. So let's set up an inequality. Next we write n is going to be greater or equal to n naught, which in our case is 20. And I'm going to write 20 in a very specific way. I'm going to write it as two terms. In fact, the two terms that we saw in our first step for finding n naught. So I'm going to rewrite this as 2 times 50 over 7 plus 2 times 20 over 7. Okay? And now I'm going to move on to the next step. If n is greater than the sum of these two terms, then I should be able to multiply each of these terms by some value less than 1, and the inequality would remain true. So what am I going to multiply these terms by? Well, with the first term, I'm going to multiply it by 1 over n. And with the second term, I'm going to multiply it by 1 over n squared. And now let's just check to make sure that this is valid. I'm saying 1 over n is less than 1. Now, is this true? Well, if you go back to our assumption, n is greater or equal to 20. So since we have n is greater than 1, then yeah, 1 over n is going to be less than 1 for all our values n greater or equal to 20. So this is the valid thing we're doing here. This implication holds. And if you notice on the first term, that corresponded to the coefficient of 50, and 50 was multiplied by n to the first. The second term corresponds to the coefficient negative 20, and on that one, the n was n to the 0th, it was the constant, and we're multiplying by 1 over n squared. So we're seeing this increasing degree on n in the denominators of our factors here. Now let's go on to the next step. We can now imply that we can maintain this inequality by multiplying both sides by a positive value. So I'm going to choose it in a very particular way. I'm going to multiply both sides by n squared times 7 divided by 2. I'm going to multiply that by both sides. Okay. So on the left side of this inequality, we now have 7n cubed over 2. And on the right side, when we divide out the factors of 1, our first term now will be 50 times n, and our second term now will just be 20. So we have 50n plus 20 on the right hand side. So you can see on the right hand side we have two terms that look like two terms in fn, except their signs are positive instead of negative. Our goal is to move these over to the left side of the inequality, but you notice on the left side of the inequality we do not have a 7n cubed. Instead we have a 7/2n cubed. So what I'm going to do is I'm going to rewrite 7/2 as 7 minus 7/2 and multiply that by n cubed. And you can just prove it to yourself. Oh yeah, 7 minus 7/2 is the same as 7/2. You have 2 sevenths over sevenths minus 1 7 over 2. That simplifies to 7/2. So we're just expanding that. And the reason we want to do that is so now we can distribute this n cubed through, and we have 7n cubed minus 7/2 n cubed greater or equal to 50n plus 20. Okay. And now we're going to move everything to the left side that's part of f of n, and everything that's not part of f of n, move it to the right side. So we'll end up with 7n cubed minus 50n minus 20 is greater or equal to 7/2 n cubed. And this should look like our definition. It should be very obvious now. So this implies that this whole left side is f of n, f of n is greater or equal to 7/2 times n cubed, and this is for n is greater or equal to 20. So our c in this case is 7/2, and as we already decided earlier, our n naught is 20. Okay. Therefore, by definition of omega, we can say f of n is big omega of n cubed. Now let's see. If you were to look at this on a graph, like on Desmos, you would probably see that this n naught is actually much larger than it needs to be. So on Desmos, you would see f of n looks something like, that's a quadratic, so it's a cubic, I'm sorry, it's a cubic, so it looks something like this is our f of n. And g of n is looking something like slower growing cubic. And where the two curves cross and f of n becomes larger than g of n is actually, I think it's around 5, but it's much smaller. But this n naught here, this value right here is like about 5, and we chose 20. So this process isn't going to give you the exact intersection, although that is something you can do since this is polynomials. From pre-calculus, you know how to find intersections of polynomials. But this is just a quick way of coming up with some n naught and some c that will show that this meets the definition. All right, so another exercise that I have a challenge for you that would be similar to this, but different enough to kind of challenge you. Show that f of n, which equals 3n cubed minus 7n squared plus n minus 10 is big omega of n cubed. So there's two differences here between what I showed you and this challenge. One is we have an n squared this time. So last time we multiplied our factor that corresponded to n to the first power by 1 over n, and our constant by 1 over n squared. What are you going to multiply the coefficient that corresponds to n squared by? Second, all the non-leading terms in the first one were negative. All the non-leading terms in this one, well, 2 of them are negative and only 1 of them is positive. So we have a mix, right? So you also want to think, okay, how are you going to approach that? How are you going to deal with that problem? But work on this, and then put a answer online, and then you can check your answer with that. All right. I hope you have a good weekend. Let me know if you have any questions.